This section is about solids of known cross-section. Another way to calculate volume is an application of integration. What we have here is sort of a top view of the function sine x plus 2. That's coming along here. And what you end up doing is, just to rotate this around, you see that we're placing squares perpendicular to the x-axis on top of this curve. And from that we're able to get a solid out of this. If I use fewer squares, of course, I get a much rougher version. So these are square slabs, or kind of prismatic, and if I increase it, and of course the idea of calculus, we use an infinite number, we get a better fit. So this is with squares, and you can see looking forward now that each one of these is a square. But we'll also do the same sort of thing at equilateral triangles as one of our cross sections. So these are, every slab's an equilateral triangle. Here every cross section is a semicircle. So there's a few different types that we will be looking at. As far as the givens for a problem like this, you have three things. You have a top view, which is defined by base functions. You have a side view, which is basically your cross-section shape, and you have to know if the cross-section is perpendicular to the x-axis or the y-axis. We're only going to be doing them vertically or horizontally, really no other options. So let's take a look at our first example. So back over here, we have the two coordinate axes, and we have the line given by 4, 0 and 0, -3. And what we're going to do is put semicircles basically perpendicular to the y-axis along these chords and everywhere in between. And just to give you an idea, we can rotate this thing along. This is how 5 of them would look. We can sweep one of them along, and you can see the area, of course, getting smaller as we continue down here. This is actually creating the solid, meaning that you add up all of these areas through integration to get yourself a volume. And we have this oblique cone. And this is the whole thing, of course. 6.28 is really 2 pi in this case. And so we're going to go through the setting up the integral to figure out how to calculate this volume. And here we are. So this is our top view given by 0, 0, 4, 0, and 0, -3. And this is an infinitesimally thin rectangle going horizontally, so this is a height of dy. This is a distance of x. This is a distance of x from an x value of 0 to some random x value. And so when we look at our side view, which is a semicircle, this is the diameter of our semicircle, because we're placing a semicircle right on top of this rectangle. So this is a distance of x. That means the radius is x over 2, and the thickness, therefore, is going to be dy. So what we can do to put together our integral, we have dy. Y, of course, is going from -3 to 0. And then we have the area of this, which is 1/2 of the circle, so it's half pi r squared, so half pi times x over 2 squared. Now we're integrating with respect to y, and we have x's, so we have to substitute. So what I do is I find the equation of this line, which is y is 3/4 x minus 3, just find a slope, a y-intercept. I can solve this for x, and then I plug this expression into my integrand, and well, first I can take out these constants as a pi over 8, then I plug in this green expression, and here's my integral, which then you can put into a calculator and solve. All of the work to do it is down here to get to 2 pi, but generally in this case the key idea is to set up the integral. That's where most of the work is, and then we can use calculator functions in order to actually solve it. Now, if instead of using semicircles, we were instead using a side view of squares, what we would see is that this x distance here is this here. Here's x again because it is a square, and so the area of this is, of course, x squared with its thickness of dy, and I would be integrating with respect to y from -3 to 0. And so the only difference between squares and semicircles, as we can see here, is the pi over 8 in front of the semicircle. If, on the other hand, I were to do equilateral triangles, then this is still x because I'm placing my triangles over here, and these are 30, 60, 90 triangles. When we split them up, this will end up being rad 3 over 2x, and so the area of this is 1/2 times rad 3 over 2x times x, so it's rad 3 over 4x squared. So when we write that as our integral, what we would see for equilateral triangles would be rad 3 over 4 x squared dy. And so note that the direction of the rectangles and the direction of the and shape of the actual top view, the base that is, completely determines the integrand and the limits, and that for a cross section we have some only the differences coming from that, where we have a square is a 1, semicircles pi over 8, equilateral triangles rad 3 over 4. It's important that you be able to derive these, because sometimes you'll have different cross sections, but it doesn't hurt to also memorize them and see how they relate to each other. So here's our cross-section comparison, and you see that if we have, this would be looking straight down on a solid, and you can see that as long as the cross-sections are similar as you go through, then you can just relate them according to these different ratios. And so if this was 1, we make this a half, and we have a square is 1 by 1, the semicircle is pi over 8, equilateral triangle rad 3 over 4, and of course an isosceles right triangle, this is a quarter of the entire square. So that's a bit of a shortcut. As a final example, we have a base determined by the intersections of the line y equals 2x and the parabola y equals 1 minus x squared, cross sections perpendicular to the x-axis that will be squares. So here's our top view. We know that we are perpendicular to the x-axis, so we have this vertical rectangle, so it's a dx. So the thickness of my square is a dx. Now the distance from here down to here is the distance from the parabola down to the line. And so parabola down to line, you have to subtract y values, or we can change them into x values. So it's going to be 1 minus x squared minus 2x. So here it is. Because it's a square, this distance, even though I've drawn it vertically here, it does correspond to the horizontal distance because we're placing the square on top of there, coming out of the page, you have to imagine. So this distance is the same as this distance over here because it's a square. We need limits of integration for x. So where do these two functions intersect? So use a little quadratic formula to find that, which leads to our integral here from 1 minus rad 2 to 1 plus rad 2, and base times height. So we have 1 minus x squared minus 2x quantity squared. If, on the other hand, you're not changing these to equilateral triangles, here's the work involved, but really the only difference at all is that you just attach in front of this integrand a rad 3 over 4. As a final example, here is a circle, x squared plus y squared is equal to 2 squared, so centered at the origin with a radius of 2, and perpendicular to the x-axis we're going to place squares. So we can rotate it around to get a three-dimensionality kind of view of it. Here's 4 squares. If you sweep one of the squares along, the idea is to be adding up all of this area to get ourselves a volume. This is what the solid would be looking like. And so in order to set this up, we have our top view, which is x squared plus y squared equals 4. We have this vertical rectangle. This distance corresponds to the bottom of my square. This is a height y. Here's 0 down to negative y. That's why this is 2y. So that's a little different than what we've looked at before. So this is 2y, which makes this 2y because it's a square. X is going from negative 2 to 2 because it's with respect to x. So my integral is from negative 2 to 2 of 4y squared dx. A lot of ways to simplify this. We can go instead from 0 to 2 and double the 4 to an 8 because this is symmetric. It's an even function we're integrating. So now I have this. Now we have to integrate with respect to x. We know that y squared is 4 minus x squared. So where I see a y squared, I would simply plug in 4 minus x squared, and you could integrate it in this manner.